and just a few seconds. So I'm assuming that you can hear me well?
Yes.
Yes.
Yes, sir.
Yes, sir.
This be good because there's fan, buzzing, and I also have, so that sometimes creates some noise. So let me share my screen. For you that I start recording. Okay, so I'll start with this thing. So this you must have already read. Okay, so I've introduced the instructors. Okay, so this course is on SMT solving and its application to formally verify deep neural networks. See, SMT solvers are they're actually a bunch of cooperating automatic procedures for deciding certain problems in logic, mostly satisfiability problems in certain fragments of logic. Now, SMT solvers have historically played a very important role in applying logic for software verification. Okay. Several breakthroughs in that SMT, the technology of SMT solving in the last 10 or 20 years have made, have allowed them to be scaled to verifying realistic software. And also, since those breakthroughs, they have been applied to lots of different areas beyond software verification. Okay, one such emerging area is applying them to perform analysis of deep neural networks and guarantee certain, give some assurance about the behavior of deep neural networks. See, when I started, I've been teaching this course for several years since I joined CMI 10 years ago. So in the beginning, I used to teach it just as, as a pretty much a logic course and with a little bit of application to the software. And then I started doing it as a combination of learning about the algorithms that go into building SMT solvers, and also applying it to traditional software verification. In the last 5 years, since as SMT solvers, the application have also been enlarged, I've been looking at every year some new areas to cover this subject in the context of applying it to some new and interesting areas. And that's where so we are. Okay, and this is one area which is quite interesting and also in some ways sexy. That is the application of SMT solvers for verifying machine learning algorithms, and specifically deep neural networks. And that's where how this course has come about. So as you can see, this is basically an applied logic course. Okay, application of logic, and specifically this particular tool, SMT solving, for this area of deep neural networks. So it is not, as I said, we've tried to make this self-containing as we can, but while it does not, we have not made the logic course as a formal prerequisite. Prerequisite, I would certainly require that you be either familiar with logic. I'm hearing some clicking sound. Can I request that people mute their mics and unmute them when you want to ask questions, please. Yeah, so although that is not logic, is not a prerequisite, it certainly will help you if you are adept at concepts from formal logic, or you're able to quickly learn about using concepts from logic to modeling and to do things like understand what satisfiability is and so on. We will be giving two lecture condensed refresher course to logic. And but beyond that, we would want you to, we'll give some references to books that are good at Hello? Can you hear me?
Yes, sir.
Yes, sir.
Sorry, the power went off here. And I'm on hotspot, so I hope the bandwidth will be, so I don't know where I was before I left. Yeah, so I think I was, so you can hear me now and you can see the screen?
Yes, sir.
Yeah, we're still live on that. So I'm going to momentarily stop sharing and I'm going to, I don't know if the recording is, yeah. So I'll make sure that the recording is starting again. Yes. So I was saying something about that this course being an applied logic course. Yes. So you don't need to understand the, a lot of theoretical aspects of mathematical logic, but you should be adept at using concepts from logic to model, software systems and be able to use these tools to do and understand what it means to model neural networks and what it means to verify software and so on. So yes, so this is a combination of three areas. One is applying logic, and we will talk two neural networks, and there are certain basic topics in what it means to formally verify software. That is something that we will cover in this course as well. And some basic things about neural networks. Now, the intent is not to cover enough basic about neural networks and also tools to build, but not the not formal theory behind neural networks and so on. So enough so you could use tools and be able to understand what neural networks do, and so you can model them using logic and do certain analysis with these logic tools. Okay, and but we encourage you to, because there are lots of resources that are available on the net about neural networks and tools and so on. So there, we encourage you to take the initiative to learn more about beyond what we cover in the class. So especially, since there is a project component for the course where the more initiative you take, the better it will be. So we'll cover the basic about neural networks, but we want you to learn more about it using resources that are available on the net. Okay. Yeah, this is the distribution of the work in the course. There will be, as you can see, more than 50% of it is on the project, which will be done in teams of 2, and that will involve some aspect of applying SMT solvers for analyzing some aspect of neural networks. And I plan to have a very brief midterm quiz, because there are certain theoretical aspects of SMT solving, etc., that we'll be covering, and I want to make sure that you are up to speed on that, and there'll be a couple of assignments to warm you up, before that. As far as the textbook is concerned, let's see. So there are 2 text books. One for covering the, let me see if I can get onto the Moodle page. So this book, so you can see the cover. Yeah,
Yes,
hello?
sir.
Yeah. So yeah, this covers all the material that we will be covering in the course with respect to SMT solving, decision procedures, and so on. So this is a soft copy, is a link to a soft copy is been uploaded. Okay, and that is for covering the SMT part of the course. Okay, and then there is for the application of this thing for particularly for neural networks, which covers the sub topics on modeling and so on. So this one is a book in progress by a professor at where is he, Madhukar? House, University of Wisconsin, is it?
Yeah, I think he's at
Yeah.
Wisconsin.
Yeah, so this is once again, both these books are, this particularly, this one is a book in progress. And so the soft copy is not meant to be distributed or circulated. So it's just for the purpose of this course. So as the topics that we will be covering in the course with respect to modeling neural networks and some of the techniques that we will be using for performing verification of neural networks using the SMT solvers are the subject matter of this book. Okay, and then there is another book. This is on logic. Okay, so there are when it comes to symbolic logic, mathematical logic, there are books that talk in a very classical way. I mean, introduces it in a very theoretical fashion, covering all aspects of logic, including completeness, compactness, and so on. But this particular book does it in a very readable fashion. Okay, in the way that's applied. Logic is applied to various branches of computer science. It's a fairly easy read, and it is written in the spirit in which we use logic in this course to actually as a means for an end, which is for verification. Okay, and so the people that want to quickly learn, beyond what we cover in the refresher on logic course, can refer to this. Okay, let me see. So there is some question. Well, I'll look into this. What happens when you click on that? No. When you say it's hello? Does it work? Does the link work? I have not heard any complaints. Now, if you're worried about the licensing aspect, I take responsibility for that. Okay. So, but are you able to does the link work?
No, sir, we are not being able to open the link. So it shows that the course is currently unavailable to the students if we click on it, like when I'm clicking on it.
I see. So if that's the case, then I will look into this. Maybe it was temporarily available, because I didn't hear any complaints the last time that I did the course. I will look into this. Okay, and I'll see how it can be made.
Sir, it's working for me, sir. When I'm clicking, it's opening, sir.
Oh, it works for you. So
Are you talking about the logic link?
No. I think he means the decision procedures.
I see.
Okay, so that may be so. Okay. So this is Yeah.
That is the problem. So decision procedures. That has
This book is a problem. Okay, so I will see if there is an earlier version of that book whose PDF can be made available to the students. Okay. Yeah. Okay. Got it. Okay. So let me then. What else do I need to? Do you want to add anything, Madhukar, Diganta, at this point?
Yeah, not really anything at this point. Yeah.
No, sir.
Okay.
Sir, I wanted to ask something. Like,
Yes.
will we be covering like simple neural networks like AI, artificial neural networks, or like more complicated ones like RNNs and LSTMs?
Okay. So you see, to begin with, basic stuff. Okay, but we will be covering modeling the RNN network also. Okay, because and that will be covered a little bit later, since some of the topics for the project might be related to RNN. Certainly, verification, how to do verification of RNN will be covered as part of the course. So Madhukar, do you have the latest? Okay, even if it's not the latest, that's okay. So here is a rough outline for the course. Okay, after today's lecture, which is just introducing and motivating the course. So we will be covering something about like the refresher lectures on first order logic and proposition logic, and then basic topics on program verification, which is the classical application of SMT solvers. What it means to verify verify programs and program correctness concepts and so on. And then the basics of neural networks, how to train them, what it means to train them, and so on. So at this point, RNN will not be covered, but later on, as you can see, we will be covering RNN verification later. Okay. Now, we haven't decided yet whether to cover RNN. I think current plan is to cover RNN later on while we discuss RNN verification. Now that you have suggested, I don't know. I mean, if maybe it is, we could move some aspect of RNN, basic lecture on RNN, what it is, etc., move upfront. What do you think, Madhukar? Okay.
Yeah, so we can either cover details about training an RNN and how an RNN looks and what are the details. But for the verification part, I don't think we'll get into so many details. We'll understand RNNs at a very abstract level and then try to exploit the fact that they are recurrent to do verification like how you do verification for programs with loops.
So see, in all these cases, okay, so while, like I said, the routine neural network as well as RNN, we will cover enough material about that to be able to understand what the structure of those networks is and how they operate and so on, so that you can, then we will be covering in detail how to model such networks in logic. That is the covered in the chapters of the other book, okay, where the verified deep learning. And there, I think there is a chapter on RNN also, I believe, okay. So to that extent, we will definitely be covering. Even if it's not there, we will be covering. But as far as covering the theory of RNN and how you build RNN, etc., that we may not be covering in full detail. Now, if that RNN verification is the subject matter of your topic, of your project, then something more will have to be done there. In most of those cases, the projects also will be on modeling existing neural networks, and in the case of RNN, existing ones. And maybe there will be, you won't be asked to build your own network and train, spend a lot of time in training and so on. So the idea is to give you access to trained networks, and then do things with them to prove properties about their behavior. So the modeling and the analysis aspect will be the emphasis. And to the extent that you need to learn something, on your own to do the project, anything extra, that is something that you will have to do by taking your initiative. Does that answer your question?
Yes, sir, that does answer my question.
Yeah. Okay, so this is roughly. So then we'll go on to cover internals of SMT solvers. So that's this week 4, and after that, then we will be covering some special procedures, decision procedures that have been designed and built for the specific purpose of verifying neural networks. Okay, so ReLUplex is one such thing, and the specialized techniques to handle to scale this technology to neural networks. Okay, and after that we introduce topics for your projects, and so this particular bounded model checking is part of the basic verification for general verification software. And then we move on to discussing a few techniques, recent techniques that are covered in papers. These are research papers, and in applying these techniques specifically for neural networks, okay, DNN as well as RNN. And those things are additional materials that you will have to will present in class, and you'll be expected to pick up from the class lectures, and as well as the papers, the supplementary papers. And of course, those things will be you'll have to read depending upon what project that you choose. You will have to supplement your reading material with those specific papers that are related to the project topic that you will be choosing. And those topics, etc., we will discuss like a month into the course. We will have start. You have to make a selection of your project topics. Okay. Once we have this decision, after that, you need to study appropriate supplementary material, and in the form of papers that are relevant for the topic of your project, and then you'll have to do that. So so that's the rough outline, timeline, and thing for the course. This has been uploaded as well, and the model, and we will, as we move along, we may tweak this a bit. Any other questions at this point before I? Yeah.
I have a question.
Yeah, please introduce yourself, your name, and then before you ask the question.
I am Ved Prakash. The data science student of first year. So my question is that do you suggest this course for someone who heard the word SMT solver for the first time and don't have a much like basic idea about the machine learning things? So and don't have any idea about neural network. So for them, do you suggest this course?
Yes. Okay. I think if anything, we will be covering enough about neural networks we'll be covering, so that aspect, neural network aspect, etc., whatever that you need, will definitely be covering to be able to do the project. So you don't, lack of knowledge about machine learning itself is not going to be a handicap. Okay, whatever that you need to know about DNNs as well as RNN will be covered in the course. But in order to, anything that you can do to learn about it with, by reading material on the internet that you can use to supplement, that will be helpful. So, there I'm pretty sure that I don't think, that will not be a handicap. Okay. It is actually the logic. If you don't have any background in logic or even exposure to discrete mathematics, okay, that can be, a bit of a handicap. Now, that's why the refresher lectures in logic I will cover immediately, starting from next week. Okay, that will be the first couple of lectures, and after that, we plan to give you some basic assignments to model using logic, and then use these SMT solvers as black box. Now, at that point, if you still are having problems in doing those exercises, that should be a warning bell. Okay, either you should, quickly get your do some learning by studying some selected chapters, which we will assign from that supplementary reading book on logic that we have, or you will have to take a decision there. Okay, so not having, once again, I don't say that a formal logic courses, I've not made a prerequisite, but if you're able to pick it up with the refresher course and doing some reading on your own, if you're comfortable with that, and then you're a quick learner of that, then I would say that you should not have any problem. But if you find that problematic, then you have to, that can be a handicap. Okay. Yeah, I think I answered more than your question. It is for people that don't have, if you have had a course in logic or you're exposed to logic, even if it's not formally here at CMI, if you're on and then you're have used logic, then I don't think you need to worry. But if you don't, then you will have to make a decision after the first few lectures. Okay.
Okay, sir.
Any other questions? Okay.
Excuse
Yes, introduce yourself, please.
Sir, I'm Abhishek Mishra from Data Science first year.
Yeah.
Sir, do we need to know a lot of machine learning or a little bit of ML for this course?
No. See, general purpose machine learning, you will not need to know. So here, what we are specifically, what we're doing is I know that there is a course on foundations of being offered by Professor KV, which runs in parallel to this course, which thing. So your answer to the question is no. You don't need to know about machine learning. We will be covering. So this is exactly the question for which I just answered. Okay. So certainly that will not be a handicap. Okay.
Okay, thank you.
But once again, I say that having exposure to logic, you will need, because you will need to, be somewhat comfortable with quickly learning about logic concepts, understanding them, and then using them to model real life artifacts. Okay. Okay, so let me now.
Hello, am I audible?
Yeah, you're audible, but
Yes, sir. Sir, I'm Saransh. I'm a student of data science first year. So, as per our timetable, this course wasn't included in our like the preliminary courses. So, will we be graded on this course as well? This was one question which I have.
will you be what?
Graded on this question. So, like for example, if we are involved in this course, so
Oh,
with our assignments,
will you get credits for the course?
yeah.
Okay, that is something that I cannot answer. I mean, you should ask that, see, because I'm not that familiar with the data sciences program. Okay, I
Okay.
think I think you would get credit for the course. This is an elective course. Okay, so this is not a core elective, by the way. Okay, this is an elective course. Just like if you take other elective courses from computer science. Oh, so Dhruv is answering something. We will have an option to credit or audit it.
Yeah, so give you an option whether you want to count it as part of CGP or not.
Okay.
And if you do choose it to count it, then yeah, you will get the grade for the course. But maybe you still want to discuss it with the faculty advisor just in case he
Yeah, I think so. I think that is what I was suggesting. My own guess is that if you credit it, you should get credit for the course. Okay, but I would first ask your graduate counselor. Yeah.
Yeah. Okay. Sure.
Yeah, for CS students and BS CS students, that's not an issue. Yeah? Okay, so I'll move on. Oh, this is not the latest one. What happened? Oh, no, this is correct, but I have not, sorry, I have not updated. This is the correct one, all right. But I haven't fixed. Okay. So what I'm going to be covering, sorry, I have not updated this. TA is Diganta. So in the remaining half an hour, I want to just introduce you to the SMT solving, what exactly it is, what it is, and thing. So SMT stands for satisfiability modulo theories. Okay, what it does is see here once again, you see I'm already introducing to certain concepts in logic. Okay, so we will get to discuss this thing in my refresher lectures, but let me start with this. It is what SMT solvers do is they are, like I said, they solve the satisfiability problems of formulas. They check if a formula in a particular logic, and that logic is multi-sorted first order logic. It checks, given a formula, if it is satisfying or not, if it is true for some instantiation of the variables in that formula, appearing in that formula. Okay. So for example, okay, I'll go quickly to examples. Okay, so here is a formula that an SMT solvers are able to solve. So it's a here the variables are all Booleans, and you're familiar with. This is just plain prepositional logic, which is part of what I introduce as multi-sorted first order logic. Okay, so. And these are propositional variables, all the variables that appear in here. So they take values 1 or 0. And what I call the satisfiability problem is checking if there is some value instances for these variables, A, B, C, Z appearing in this thing, such that this formula makes it true. Okay, that's what is called as a satisfiability problem. If there's no such I mean, if this is true for every instance, then it is usually called the formula is valid. Okay, when people say satisfiability problem, it includes validity checking, as well as if there is no, this formula is not true for any instantiation of the variables, then it is called unsatisfiable. Okay, that's what SMT solvers do. In this case, the formula is from propositional logic. So the satisfiability problem of propositional logic is called Boolean satisfiability, and the solvers that only do solve Boolean satisfiability, they are called SAT solvers. But SMT solvers allow you to make the variables in the formulas range over other data types. What I call as sorts here are actually considers other kinds of data types like arithmetic or strings or other kinds of things, or bit vectors and so on. So here is another formula that an SMT solver can check the satisfiability of. Now here, the variables are a Boolean combination, a Boolean combination where the atomic formulas are equalities or inequalities, a negation of equalities. Okay, so all the variables here are assumed to range over, say, real arithmetic. Okay, so the question of whether there are instances for the variables, the arithmetic variables here, real values that make this thing satisfy. So that's an instance of an SMT problem. Okay, here is the same thing, where I'm assuming I and j are a range over natural numbers. Anyone fathom to guess if this formula is satisfiable? The one that I've highlighted?
It's not.
Why? Can you explain?
Because j plus I equals j would imply I being 0.
Yeah, that's right. So, but the other constraints here don't allow I to be 0. Okay, so this is unsatisfiable. Therefore, that is a satisfiability problem. So that's what SMT solvers do. And similarly, you can have, see, this particular thing, is also an LP, integer linear programming problem, because it consists of, let me see, so there's a question here. This is like Prolog stuff. Okay, Prolog is a little bit more than this. Yes, it is somewhat related to Prolog, but I will see Prolog has, by the way, Prolog is a logic programming language for those of you who don't know. This question was about Prolog, but Prolog is different in that there you are, the emphasis is on execution. You have logic, you write programs as in some fragment of a logic, okay, which is actually quite restricted, so they are called Horn clauses, okay. They are special, form of thing. And then but it is execution oriented. Yes, it can be considered as it does use some things in a more restricted versions of SMT solvers for defining, executing those programs and searching. So yes, that is, I would say, is an application of you could call some restricted form of SMT solving. But here we are, using SMT solvers not just to execute programs, but rather to solve problems, okay, that are related to program analysis. But in this particular course, for modeling and analyzing neural networks. Yes, there is a relationship. Yes, that is true. But here is, okay, so once again, as you can see, this is once again linear integer arithmetic. I was about to say that here is this particular formula is an instance of an LP problem because it is linear inequalities, a conjunction of linear inequalities, which is exactly an LP problem. Okay, and so is this. Okay, but like I said, SMT solvers do more than that. For example, here, this is not a simple LP problem because this has Boolean. It has more complicated Boolean structure. Okay, so SMT solvers are able to handle these kinds of any combination, Boolean combination of these atomic formulas over the various data types. Okay, so yeah, since neural networks are primarily they operate on real valued, real valued. So primarily we will be dealing with SMT formulas over arithmetic sorts, but SMT solvers are also applicable, as I mentioned, to other kind of data types. So for example, here, this is it's an array, which is like a function, and you can have the index ranging over some finite precision arithmetic. Then maybe the range is infinite precision arithmetic. So, and such combination of theories and Boolean formulas, formulas over such data types are also fair game for SMT solvers. Okay. So this is roughly what SMT solvers do. Okay, and as I said, SMT solvers, SMT stands for satisfiability modulo theories. Okay, this is satisfiability. If it's just Boolean satisfiability, it is, just propositional, then it is Boolean satisfiability. But here, since this satisfiability problem is over theories that describe other types, that's why it is this modulo theory thing is there. Now, what is, I said first order. Okay, the multi-sortedness, I hope you understand. It is coming from the fact that SMT solvers, the variables in the formulas can range over multiple types, and types are used as sorts. So what is first order about it? Okay, when you hear first order logic, okay, whenever the variables here and the quantification of those variables, the variables, when they are quantified, if they're ranging over the objects that belong to these sorts, then they are then such a logic where it allows the variables only to range over those elements over the chosen domains, then it's called first order, as opposed to higher order logic, where you're allowed to quantify over the variables, can range over functions or relations and sets of sets and so on. That's what this first order is. Okay, where it comes from. So as you can see, all of formulas here actually they happen to not have any quantifiers. They were actually quantifier free. Okay, and all the variables were ranging over first order elements or object. Okay, so all these formulas here are quantifier free because there's just no quantifiers. Okay, and so this one is usually SMT solvers are very efficient for quantifier free fragment of first order logic. Now here is, but SMT solvers there are extensions that can solve quantified formulas as well. So here is an instance of such a formula. Okay, so where you have multiple nested quantifiers here, and in this case I call it QBF, and if they are ranging over Boolean variables, then it is fairly simple. But just imagine if you allow these variables to range over arithmetic data types and other data types, then it becomes in general an undecidable problem. But there are, even with quantifiers, some fragments of logic. One such instance is called Pressburger arithmetic, where it is decidable, and SMT solvers are able to handle such things. But these are very hard problems, complexity-wise, and therefore SMT solvers in practice, they primarily are used for the quantifier-free fragment of first-order logic, but there are extensions to apply them to quantified formulas as well. So a bit of a brief history of so I'll go till 4:45. Okay, so that's the idea. So early tools were all developed, so the primary driving force, as I mentioned, for SMT solvers were, software verification. Okay, there is an area called theorem proving as well, which is also the prime mover for it was software verification. So, so it has followed those, these developments of SMT solvers happened at those places and those universities and research institutes which were where there was a strong groups working in program verification. And Stanford University happened to be one. And Stanford Research Institute is also something that is close by. It's a research institute. And that's where some of the early decision procedures got developed. MIT was another place as well. Okay, since then, technology has gone through, there's a lot of breakthroughs in the basic algorithms behind these things that SAT solvers, the Boolean version of it, is now is quite widely used in practice. Okay, so this kind of shows how SAT solvers have scaled in their application to real problems. So the the scalability here is measured, the parameter, in terms of the number of clauses. I mean, I'm sure some of you are familiar with clausal normal form, okay, where any Boolean formula, proposition formula, can be expressed as a sum of, a product of sums, okay, that is CNF. So the number of, clauses, okay, that is one measure, the number of sum terms in the formula, and the number of variables, then zels, that appear in the formula. Those are the two parameters that determine the complexity of the SAT solving, and so is SMT solving. So as you can see here, so how they have scaled over the years in terms of number of clauses that they're able to do. So, and there is you can see, especially in the number of variables, there's a sudden definite inflection point around 2000, okay, and around 2000 and 2010, and that is with good reason, okay. And there were some very good heuristics and engineering that went into this technology that made it scale multiple orders of magnitude. Okay, and that's what has made these things now readily applicable in practice. Okay, so some of the tools, the leading tools are here I've mentioned some, and the organizations that have architected these tools. Z3 Microsoft Research is certainly one leading institute that is behind, and that CVC4, this is an open source tool, okay, and this is from SRM. All these are SMT solvers, which means they subsume inside them, they also have a SAT solver, okay. So applications of SAT and SMT solver. So as I told you, traditional program verifications and more recently program synthesis have been the driving force. So, but there are also beyond software verification, constraint solving in general, okay, configuration management, robot action, planning, compiler optimization, and of course, hardware and program verification. Those are something that I would call as traditional things. And more recently, as these things have scaled up, including SMT solving, they are now, when they become SMT solving technology has also advanced, they are being applied to more sophisticated or varying areas, as varying as computational biology, and as we will see in this course, to neural networks and an analysis of neural networks. Okay, what kind of analysis? How do you model? Those are the subject matters of this course. Okay. Any questions? I'll pause a moment here. Taking any questions? Okay.
Sir, how would you use SMT solvers in computation?
Please introduce yourself. The name, please.
My name is Harsh. And like my question is like, how would you use SMT solvers in computation biology?
Okay. How would you use in computational biology? For example, system biology, if you're familiar with system biology, where to model the interactions, okay, among various, that is one way that is it is used. You can model them, and then you can analyze the way that these molecules move around, okay, and then accomplish certain biological tasks. So you'll have to model the transmission of various proteins across biological network, okay, and so that then there are certain reactions, for example. Okay, those reactions happen as per certain rules, okay? And those certain reactions may be good, certain reactions may be bad, okay? And you want to predict the chances of certain reactions, unhealthy reactions, undesirable reaction, what the chances are, and so on, okay? So there, it goes beyond discrete logic of SMT. SMT solvers, at least in this course, they are all, the domains are all discrete elements. I mean, there is continuous elements also, not necessarily discrete, okay, but they are really combined. So what I'm saying is you may end up, because they're probabilistic outcome in biology. So there'll be Markov decision procedures and so on. Okay? So that are, and there is SMT layer on top of Markov decisions. That is also a direction in which this SMT solvers are used in computational biology. Okay, so briefly, that's all that I can answer. Yeah. Okay.
Okay.
I'm going to skip this. This just shows kind of the applications that made different SAT solvers possible. And as you can see here, it's only since like 2007, 2010 that you see SMT being coming into the forefront, the picture, where this application like bio, etc., are coming into the picture, because it's only recently, when compared to SAT solvers, that SMT solvers are even came close to being to scale to some reasonable things. And even now, SMT solvers are not very efficient compared to SAT solvers. Okay, but one point is, see, whatever that you can do in SMT solver, mostly as long as your domain is finite, you'll be able to encode it using Boolean logic and able to solve using SAT solvers. Of course, that encoding itself may have an exponential blow up. Sometimes, although SMT solvers are not, the decision procedures involved in SMT solvers are certainly not as efficient, because those decision procedures complexity are much harder in the NP, much harder than being NP hard. But when you encode them using multi-sorted logic, the size of the encoding can be very compact. Okay, so you can have an exponentially smaller encoding of the problem that you're trying to solve, and therefore sometimes SMT solvers can win over SAT solvers. Okay, and that happens in more sophisticated applications. Okay? So yeah, so it's only recently that SMT solvers have been thrown into this application mix. So in the remaining 10 minutes, I want to just look at some traditional applications. Okay, in the next class, we'll look at what it means to model this logic, tidbits of which you have already seen in the examples that I've shown, to neural networks that Diganta will cover in on Thursday. Okay, so here is one application. So I mentioned configuration management. So here is the problem here is deciding if a component can be installed with some resource constraints that are given. So here, so each box here represents a component. Okay, it could be a software component or some mechanical component or whatever. So the solid, the arrow here says that A, in order to install A, you need, since it depends, you need all B, C, and Z. Okay, that is what this arrow means. If there's an arrow with a dot here, that means that C, in order to install C, you either need D or E. Okay, one of the two is sufficient. So this arrow, red arrow here, means that there is a conflict. You can't install, you can't have both D and E installed simultaneously. Green means Z is already installed. Okay, with these constraints, and you want, suppose you want A to be to install A. So you want to. The problem is to see what is the optimal set of components, okay, whether it can be installed with these given constraints, and if so, what is in some sense the optimal, maybe the smallest number of components that you require. Okay, so this is a classic problem, of Boolean satisfiability. Okay, so which is also part of here. So here, so we are modeling each variable here, A, B, C, corresponding to each component here, means that if that is true, that means A is installed. Okay. So this dependency that A depends on B, C, and Z is can be modeled as an implication. That is, for A to be installed, you need B and C and Z to be installed. But for C, what you need is either E or D, as well as one of F or G, and that's what this constraint. So here says. Similarly for D, needs a D, and this constraint that D and E cannot be simultaneously installed can be modeled as you can't have both D and E. Okay, you can only have one of D and E. And the whole thing is, you want Z is already installed, therefore Z has to be true. And you want A, the goal is for A to be installed. So now this entire question formula models that situation, okay, that you want to solve. So if there is some instantiation for these variables, 1 or 0, that makes this entire formula true, that means then that A can be it is possible to install A with the given constraints. Okay, and any such satisfying instance is a possible solution for the problem that you have. Okay, so this this can be solved. Snap of your finger. This by an SMT solver. Okay. So here is a problem drawn from program checking equivalence of two programs. Okay, so here's a program that computes square, two programs, both of which compute squares over integers. One does it in kind of a sequential, sequential way through some series of assignments. The other one does it in a more direct way. Okay, just a cooked up problem. Okay, but this can, variation of this can appear in real thing. For example, compilers, when they compile programs into other programs, compiler correctness is very much an instance of showing equivalence between two programs. So this can once again be modeled as an SMT formula. When I say model as an SMT formula, what I mean is it can be modeled in this quantifier-free first-order fragment. First-order logic. Okay. So what we're modeling, what this formula on the right side models is that if you supply the same for equivalent inputs, the output of the two programs are equivalent. That's what this thing is saying. Okay. So, and all these, this says that it models the effect of assigning y, assuming that the input value for y is y naught. Okay. And so the output of function 2 is R2. Okay, so that is directly computing. So if our R2 is y naught squared, here this is modeling each assignment. Z gets the value y naught, y gets x naught, and so on. And finally, the result value is returned by the function 1 is R1, is modeled by this logical variable R1. And that is computes whatever x1 times x1. Then you have to, what you have to show is that R2 is equal to R1. And we have expressed the negation of that and then seen if this is satisfiable. So if it is, the two are equivalent on all values, then this one has to be not satisfiable. Okay. If they are equivalent for all values. Okay. So I have expressed that equivalence checking problem as a unsatisfiability problem. Any questions here? Yeah, this should give you some idea. I mean, in your first assignment, okay, we will make you go through, solve some of these things using using Z3, okay? So that way you will, when you do things on hands-on, you will see how naturally these concepts can be expressed, it can be used. I mean, these logical concepts can be used to model, okay? And that will give you some idea as well. Yeah.
Sir, I want to know, like, how practical is this program equivalence checking? Like, for example, let's say I want to check if a brute force algorithm is equal to some optimal algorithm. So, like, how practical is it to use SMT solver? Like, how long does it take to answer for like some non-trivial program?
Yes. Okay. So that's a very good question. So I think how do you measure that in terms of lines of program? Okay. So the question depends, I mean, on how the scale. Okay. So your question should be answered. I mean, how big a program can be these things can be used?
Yes, okay? Let's say like 300 lines of code or 400 lines of code, something like that.
Yeah, correct. So that depends on how different the two things are. Okay, they are structurally different. See, if you just take some two arbitrary programs and try to solve them, and then if there are hundreds of thousands of lines of code, okay, these formulas become too big. Even with although they are, those graphs that I showed you show that these things scale for hundreds of thousands of clauses and several millions of variables. Okay, so these encoding methods can become those formulas that can grow very big very soon. Okay, so I'll answer it in an indirect way. If as long as these you have to exploit. Okay, so as long as you can encode the problem in terms of that that you're able to, then you can solve it. But before you do that, it depends on how close your programs are. Okay, structurally, and then you have to use some clever methods. Okay, to eliminate redundancies and so on. And with those kinds of clever methods, you can scale it to, there are instances where they've scaled it to, certainly in some cases for, tens of thousands of lines of program. And in very rare instances through decomposition techniques and so on, some hundreds and thousands of lines of program. But there's a lot of clever pre-processing that you will have to do to ensure that the resulting formulas that you get are within the capability and the capacity of present-day SAT and SMT solvers. Okay.
Okay.
So that is why just learning SMT solvers in theory, it really is not very interesting. You will have to study some application, because there are then you have to study it in in combination with these kinds of techniques that you can use for encoding, modeling, as well as scaling these things. You saw probably in that course outline, in the timetable, we had keywords like abstraction techniques. Okay, those are very key. Okay, how you keep the essential information when you try to do this, when you try these kinds of applications, and which ones you throw away. Okay, then you can see you can do wonders. Okay, and therefore those techniques are just as important to allow these abstraction and other kinds of meta level logical techniques are just as important as SMT solving techniques. And that is also an important subject that you will learn, okay? Specifically with respect to scaling the application to neural network analysis.
Okay.
That's a good question. Yeah, finally, so here is like what you said, so here is a compiler optimization problem. It is not exactly, it is not as general as an equivalence problem. So here is, this is a compiler optimization that almost all compilers use when it comes to processing arrays. Okay, so here there is an array assignment inside a for loop. Okay? And for big arrays, for big arrays, even the select operation can be quite expensive. Okay, so you want to optimize on the number of selections into arrays that. So here you will be, doing as many access as for every element, the size of the array. But if the right-hand side here does not change, that is A of j, does not change. So you see, j is never modified in this. Therefore, A of j for all, throughout for all iterations, is like a constant. Okay, and therefore you can move this right-hand side expression outside the loop, make one single assignment, and then have that use that as a constant here. Then you will reduce the number of array selections that you make. But this optimization is sound only if j is not modified in the body of your code. So this formula here, which you actually saw earlier, this is one of the SMT formulas that I used as an example, ensures exactly the condition, okay, that is necessary and sufficient for performing this optimization. This is violated, then you cannot do this optimization. So here I is ranging over some arithmetic values, and yeah, so this kind of things that SMT solvers can do. I think I'll stop here, okay? And take any questions that you have. I went a few minutes beyond 4:45. Any questions here? Okay. Then, do you want to add anything? Madhukar? Diganta?
Yeah, no, sir.
Yeah. Yeah. Next class is on Thursday. You know, since Madhukar and I have some prior commitment, Diganta will be taking the course. I mean, taking the lecture. Okay. So he will be covering let's see. So he'll be introducing neural networks. Okay. For some reason, I'm not. Back to this thing. Yeah. This one. Okay. So he will just use a simple neural network. Okay. Very small example he'll introduce and then take you through the steps of, you know, what you need, how you could model using as them a neural network as formulas. It's a quick, very quick introduction to what DNNs are, what it means to model them in logic, and what it means to actually analyze or specifically prove some properties that are of interest for DNN. So please do attend. So that will give you an idea of very clear idea of what this course is all about. Okay, since the DNN aspect also will be covered. In a very, very simple way. And then, of course, he will be covering it in more detail later on, after I do a quick refresher of first order logic. Okay? Okay, good.
So Thursday, same time, 3:30.
Say that again?
So Thursday, we have class at the same time, 3:30 p.m.
Correct, exactly right. I mean, unless I hear a lot of complaint, as I told you, there is a clash between this and KV's course. Maybe there are some people who want to take that as well as that is foundations of machine learning. Okay, now I don't know if there's that conflict is a big deal. Now, you know, so I will let this settle until people. I have a core group of people that really want to take the course, and then if there are conflicts, I can work around depending upon the constraints and so on. But for now, yes, 3:30. Yes.
Thank you, sir.
Thank you. So I'll stop sharing, stop recording.